All right, guys, this will be the solution to the AP Physics 2 Unit 2 review for response questions. This will be for question number 1 first and then question number 2. All right, let's get to it. All right, so for this first question, we've got a piston cylinder arrangement. We've got a piston that can move back and forth. Inside the cylinder is some ideal gas. We are able to measure the temperature and the pressure inside of this through some kind of pressure probe. So this is an experimental setup. And the sample of gas is taken through a 3-step thermodynamic cycle from A to B to C and then back to A. In process A to B, we're going to decrease the volume to 1/4 of its original value, keeping the same constant pressure. B to C, we're going to expand back to its original volume isothermally, and then C to A, the gas returns to its original state without any work being done on the gas. So the first part of the question says, on the axes below, draw a graph of pressure and volume between these 3 steps. All right, so first of all, between A and B, it says we're going to go to 1/4 of the original volume. So if this is the original volume at A, 1/4 of that will be 1/4 as big. So that's going to be over here. So we're going to end at 1/4 volume of A at that point. And it's going to be done while the pressure is constant. Okay, so that means it's an isobaric process. And so we have to draw a straight horizontal line from A over here to this new point, which I'm going to label as B. That's our second point. And it is important to draw the arrow to indicate the direction of that motion. Now, in the second portion, it says that we're going to return back to its original volume isothermally. So that means it's going to be some kind of a curved line that goes down and to the right. Now, we don't know exactly where it's going to end up yet, but it's going to be some kind of a curved line that goes down. So what we need to do is we need to figure out what that final pressure will be given this specific volume. And then lastly, it says we're going to go from C back to A, so C will be down here somewhere, back to A without any work being done, and that's a constant volume process, so we're going to go straight back up. So let's figure out what that pressure will be at our point C down here. Somewhere down here is going to be point C. So the way we do this is that we consider, because it's an ideal gas, we can set up this little relationship between the different states of the gas. Pressure at A, volume at A, over the temperature at A has to equal the pressure at B times the volume at B divided by the temperature of B, which is also equal to pressure of C, volume of C, over the temperature of C. All right, so from the given information, it tells us that the volume at B is going to be 1/4 the volume at A. So what I'm going to do is I'm going to take these two statements and make that substitution for the volume at B. So I got pressure at A, volume at A, over temperature at A, and that's going to equal the pressure at B times the volume at B, which we said is 1/4 the volume of A over the temperature of B. All right, so this volume of B term is turned into 1/4 volume of A. And so what that does is it allows us to get rid of our volume of A term. Now, it also tells us that the pressure at A will be the same as the pressure at B, because it's going to be an isobaric process. That's what it says. We're going from A to B across this line from A to B at the same pressure. So that means that the pressure of B, this term right here, is exactly the same as the pressure of A. So if I make that substitution, my pressure at A term goes away. And that leaves me with 1 over the temperature of A has to be equal to, well, there's just 1/4 right here. I can bring the fourth down to the bottom. 1 divided by 4 times the temperature of B. And so that means that our temperature of A is 4 times the temperature of B. And that makes sense on the graph. Anytime you're farther to the away from the axis, the temperature is hotter over here typically than it is over here. So we're at a higher temperature at A than we are at B. 4 times as much. Now, let's look at what happens between B and C. Well, between B and C, we know this information. We'll rewrite that: pressure at B, volume at B over temperature at B is equal to pressure at C, volume at C over temperature at C. Well, because the statement says that going from B to C, we're going back to the original volume isothermally. So that means that these two temperatures, T and TB and TC, are the same. And since they're the same, they'll end up canceling. Now, we also know what the volume at B is. It's 1/4 the volume of A. We've already said that. So I'm going to make that substitution for volume of B. So pressure B times 1/4 the volume of A has to equal the pressure at C times the volume of C. But in the statement it says we're going back to the original volume of A. So that means that this term right here will be the volume of A. So I'll make that substitution, volume of A. And so what happens here, once again, our volume at A goes away, and we can conclude that the pressure at B over 4 is equal to the pressure at C. All right? But once again, remember that the pressure at B is the same as the pressure of A, so the pressure at C is 1/4 the pressure at A. And so that'll allow us to find out what pressure state C will be in. It's going to be at 1/4 the pressure of A. That's what we said back here. 1/4 the pressure at A. Oops, sorry guys. 1/4 the pressure at A. So our point C is right here. Oops. All right, now all we need to do is finish drawing in our lines. So we go from A to B, go isothermally to C. That's why we have this little curved line, and then back up between C and A, back up to A. All right. And that question right there, this was actually an old AP Physics B question, but I've seen questions like this on practice AP Physics 2 questions. This is actually worth 5 points. All right, you got 1 point for that isobaric line, 1 point for the isochoric line, 1 point for the isothermal line, 1 point for recognizing that the final pressure down here is 1/4 the pressure at A. So you got 1 point for that. And then you also got 1 point for labeling this at 1/4 the volume of A. So 5 separate points you can get on that. All right, question B says for process CA, is the net flow of energy into the gas or out of the gas? Explain your reasoning using physics principles. Describe one method by which this flow of energy could be accomplished in the laboratory. I would say that if this is on a Physics 2 test, this would be equivalent to some kind of a free paragraph length response where you got to explain it. So for, I missed part 2. Let's do part 2 right here. For process BC, is energy added to the gas by heating or removed from the gas by cooling? Support your claim. All right, so for what they're looking at is this isobaric process between A and B. Between A and B. So what's happening here is the pressure's going, or the volume is going down, but the pressure is remaining the same. So since you're losing any kind of volume, then that means that you have to be taking energy away from it. Because if you remember, work is equal to the pressure times the change in volume for an isobaric process. Well, if this volume number goes down and pressure is being held constant, the only way for that to happen is if the work number goes down. And because work is an energy term, and this delta V is getting less than, in other words, it turns into a negative value, pressure times some negative volume change, it has to be concluded that the energy is being removed, right? And so you're doing that through cooling it off. You're just making that cooling. All right, so now back to question B. For process CA, this is where we're going up from C to A, all right? We're going up. We're gaining pressure but keeping the volume the same. So that's like putting a Coke can or something on a campfire. You know, you're adding energy to it through heating, and you're keeping the same volume, but the pressure is definitely going up. It's a pressure cooker, essentially. Is the net flow of energy into the gas or out of the gas? Well, that's obvious. You have to be adding energy into the gas. All right. So the idea is that when you're adding energy into this gas through heating, there's some fire down here, you're adding internal energy without really changing anything. And the only way that we can really do this is if we lock this piston in place. So you put some kind of clamp on it, or you'd have some kind of tightening or whatever. But that is a method by which you could do this. Now, how do you do it in the laboratory? Specific words here. You could run it under some hot water, put it over maybe a really low temperature Bunsen burner or some kind of a flame heater or something like that. You could even just get a hairdryer and put on this. As long as that piston is locked down, you can add energy into that gas by means of heat. Now, part C asks, we've got these two curves, and it shows the distribution of particle speeds of the sample of gas in two states. Curve 1, a state that occurs before curve 2 as the gas goes through the cycle, which states corresponds to curve 1. So in other words, what they're trying to do is say, well, curve 1 corresponds to A, B, or C, and curve 2 corresponds to A, B, or C. So they're trying to link this picture to your states A, B, or C. All right, and so this is kind of how I stated it. I said that curve 2 represents particles with a higher peak average speed. So if you look at your graph, kind of sketch this out real quick. Curve 2 is kind of lower, but this peak is kind of basically in the middle of the graph right here. And so that peak value right here corresponds to an average speed that's somewhere in the middle of this scale. But curve 1, its peak is way over here to the left. And so it's the molecules here, the average speed is less than the average speed of 2. And if you remember, temperature is related or proportional to that average speed of the molecules. All right, specifically, kinetic energy is equal to 3/2 times Boltzmann's constant times the temperature. And so that speed term is in here. Specifically, it's a v squared, 1/2 mv squared. That v term, the higher that average speed, the more temperature you have. So that means that right here, this is hot gas, and this corresponds to a cool gas. All right. So that means that curve 1 has to correspond to a low temperature, and curve 2 has to correspond to a hot temperature. Well, since B and C are on an isothermal line, then that means that temperature of B and the temperature of C are the same. Okay, well, are these temperatures hotter or cooler than temperature of A? Well, it has to be the case that temperature at A is hotter, because if you remember when we went over here to C and I added heat to it, I moved it up to state A. So I'm adding heat between C and A, so that means that it has to be the case that temperature of A is greater than the temperature of B and C. And you can even go back to our original formulas back here at the beginning, that the temperature of A is 4 times as hot as the temperature of B. So that means that this hot gas has to correspond to state A. The cool gases have to be either state B or C. They're the same temperature, you don't know which one it is. But you can kind of reason it out, because the process, the order of this process goes from A to B to C to D. That's the order. Or not D, back to A, sorry, back to A. So which step would go from a cool gas to a hot gas? Well, it can only go from B or C to A. And the only time that can happen is if I go directly from C to A. So ultimately, what you conclude is that curve 2 belongs with state A of the gas, and curve 1, which comes before curve 2, has to be C. State C of the gas. All right. Now, just kind of real quick, let me go over the points for these other parts. For this first one, part AI was worth 5 points. AII was worth plus 3 points. For question B, this was worth plus 2. And for question C, this particular question was worth another 2 points. So this was an old physics, actually I have it up here as 12 points. 5, 6, 7, 8, 9, 10. Yeah, 12 points. All right. So that concludes the solution for the first question. If you have any issues or you need to ask me about it, just send me an email. Thanks a lot. Bye-bye.